next speaker is Jesper, who's going to pick up on this theme and tell us a bit about GravityCam, a proposed instrument for the NTT.
Yep, worked. Okay, so I'm going to talk about the GravityCam, which is an instrument proposal for the NTT in Chile. So first of all, thank you for Craig for giving a very nice introduction to my talk. So as you all know, the problem with ground-based imaging, high-resolution imaging, is the atmosphere, which makes the PSF smear out the light from the stars. So as Craig was talking about, if you do high frame rate imaging, you can do shift and add, and you can improve the resolution of your instrument quite dramatically. Here shown in the bottom here, the top blue curve is the 10 times a raw exposure, long-time exposure, and if you do high frame rate imaging and just do simple shift and add, you can get a 2.5 to 3 times improvement, and on the NTT that would mean that you could get just 100% selection and do tip and tilt correction. You can get down to 0.3 arc seconds generally, and of course with higher selectivity you get even better resolution and higher Strel ratio. So using that, we have proposed a new instrument for the NTT. It's basically, we call it GravityCam. It's basically a large array of high-speed detectors. And with that, we will be able to do high cadence surveys over a large part of the sky. This has a long list of science drivers. Exoplanet detection via the microlensing methods, weak shear studies for dark matter detection, a lot of database for stellar variability and solar system science. So, and also the instrument will be very complementary to the Son of X shooter spectrograph as a high resolution imager. As said, just by doing high frame rate imaging, we can get high resolution over a much larger area than adaptive optic systems, and basically have the high resolution over the full half-degree field of the NTT. And the approach we have shown to work before on another instrument using an EMCCD camera is to create a very high resolution reference frame using the very best of the short exposures, and then using that reference frame to reduce the data from by stacking all the frames to get a very high signal-to-noise science frame, and in that sense you'll get both the high resolution from the log imaging, and you get the good photometry from using all your data. And the goal is to create like a public archive for data mining, where you in a single pointing you get different data products at different cadences. So you have the 25 hertz 40 millisecond cadence. You could get like 1,000 stars with very high time resolution. You can stack those and get 10 to the 4 stars with slightly higher and so on, and then you can get up to 10 to the 7 stars with much lower time resolution. So you can really get a huge archive with different cadences and photometry, and you can use that for whatever purpose you have. So just to go a bit into the science drivers, so the microlensing method is, here's a very old observation, one of the first discoveries of a planet where you have a high, you get a large bell curve from the photometry of two stars aligning and giving you a lensing event. And if there is a planet orbiting the lensing star, you get a little bleep on the light curve, which can be analyzed. And we, in this case, we found a 5 Earth mass star, Earth mass planet around orbiting the star. And here you can see how much, if for a 1 Earth mass star, what the magnitude difference would be, and how far the blue curve, and for how long you would have to observe it. And you can see the red curve shows you what a lunar mass star at a 1 Earth radius signal would look like. So for GravityCam, we will be able to go 4 magnitudes deeper than OGLE, which is the leading survey, microlensing survey telescope at the moment. And we could, with the right cadence, actually reach and detect lunar mass planets. With GravityCam, you can probe an area, so you can find more Earth-like planets than any of the other planet-finding methods that are currently available. So another science driver is the dark matter, that with the high-resolution observations, you can improve on the weak lensing observations from the ground, which can complement the Euclid space mission, which is the biggest, will give the biggest improvement to that area in the near future. Because we have a much larger collecting area than Euclid, and we have much better knowledge of the PSF over longer life, over the lifetime of the instrument. Whereas in space you have radiation damage issues, which affects your PSF, and you have longer exposures, so you get brighter fatter effects, which is not an issue for GravityCam, which always do very short exposures and therefore don't have the brighter fatter problem. The last science driver I will show is the solar system science, where we have the advantage of having a high spatial resolution, which can be used to resolve the binary orbits, and it allows for mass measurements and density and composition constraints. The high time resolutions means that we can actually measure the sizes and shapes of minor bodies as they are called background stars. And an example here is given occultation that was observed by the EMCC instrument at the Danish telescope in Chile, where we found 2 rings around an asteroid which was never seen before. So with GravityCam, we'll be able to do these sort of observations, but we'll also get a lot of these observations for free, as it will be part of the microlensing survey. So by analyzing the survey, we might be lucky to find these without actually looking for them. Well, beforehand. So they sort of come free, and we'll be in that way we'll be able to find smaller objects and very distant objects, which would not be possible to observe directly, as they would have as they would be so faint, and all of this can be used to get a better understanding on planet formation and the theories in that sense. So these are, we still haven't done a phase A study, I should say, so these are just ideas that are discussed, that we would put the GravityCam on the Nasmyth port of the NTT. There's good optical quality, there's plenty of room for such an instrument, and to be able to observe in a wide bandpass, there would be need for a atmospheric dispersion corrector, and also we would need a filter wheel to do for micro-lensing survey is achromatic, so it can be observed in a wide band, but other science cases might need more narrow band filters, so a filter will be needed for that. So the NTT, as I said, has a field of view of half a degree, and it's very important for the optical design to have a good optical quality across the entire field of view. So that's a major challenge to do a good optical design for that, and the front plate of a cryoduer where the focal plane should reside would need to be a field flattening optical device. So the Nasmyth focus of NTT has a plate scale of about 5 arcsecond per millimeter, and this means that if you put a detector with a pixel size of between 10 and 20 microns, you get a pixel scale of about 0.05 to 0.1 arcsecond per pixel, and that's around the diffraction limit of a 3.6 meter telescope in the visible range. And depending on the pixel size and fill factor of the devices, you would need about 100 million to a billion pixels to fill out the focal plane. So we're talking a focal plane using somewhere between 50 and 200 devices. So it's going to be a really, really big instrument with a lot of devices and a lot of electronics as well. The initial idea of the detectors to be used was electron multiplying CCDs. The problem with those are they due to the charge transfer, frame transfer area that is needed and quite large packages, they will only have a fill factor about 1/6 of the focal plane, which means to cover the whole field you have to do 6 pointings. CMOS imaging sensors has been developed quite a lot over the last couple of years, and they are now starting to become good enough for use in astronomy. And the first, there's a couple of astronomical instruments at the moment using CMOS devices. With back thinning, they can now have quantum efficiencies very close to what CCDs are offering, and new high-row technology can improve the near-infrared quantum efficiencies of CMOS devices, which will be very useful for GravityCam. As you can see, you can get very far out into the near-infrared and really improve that. So, as you probably know, CMOS has charge to voltage conversion in each pixels instead of as a CCD where it's done at the readout node. So it means that they can run much faster, and they can still at a low noise level. So you don't need the electron multiplication as the EM CCDs have. And as they run in a much lower power level, and the new devices, new CMOS devices has on-chip analog to digital conversion, you can simplify your readout electronics, and this whole system will become much easier to build and to maintain if you use CMOS devices rather than eMCCDs. And also they come in in highly buttable packages. There's an example of a large CMOS device here, which can be 3 sides butted, and that means that you can have a much higher fill factor of your focal plane, so you can observe the whole, or 80-90% of your pointing of your field of view in one pointing, which will increase the efficiency quite a lot. One problem you can have with the CMOS devices is they have because each pixel has its own charge to voltage conversion. Each pixel will also have its own noise and its own gain value, and this might make the photometric reduction of the data more difficult, or is definitely something that needs to be put some more work into. At the Open University, we're currently building a test camera for a CMOS device. It's the SIS120 device from E2V, quite a standard 2K by 2K device with 10 micron pixels and a 20 Hz frame rate. The idea is to test this and compare it to the eMCCD technology to see how it compares on a known technology for astronomy on a range of parameters. And then we will go to the Danish telescope in Chile, where we will install the CMOS test instrument next to a eMCCD instrument and do a direct comparison of the two technologies. The Danish telescope happens to be on the same side as the NTT, so that is quite convenient. And we're planning on, hopefully we'll have the test instrument ready this summer and can go to La Silla in this summer. And so the main purpose is to test the detector technologies for GravityCam, but also to sort of establish the readiness of CMOS detectors for high-speed astronomical imaging. One of the big things and issues, or it has to put a lot of work in, is the data analysis. We will have a very large focal plane, as I said earlier, and high-speed imaging, so we will have many hundreds of terabytes of data coming in every night. This, of course, is not possible to store all this, so it will need to be real-time analyzed, and it will have to produce different outputs for different science cases. The good thing is that this can be optimized very well for GPU processing, and the idea is to create a fixed reference frame for each pointing, a high resolution reference frame, which we then reduce the images and put them into these appropriate resolution bins depending on the resolution we get for each frame, and then create line curves, which for a microlensing survey we would need. You see the time stamp is days or hours, so that's 1 point per 2-minute observation. However, if we find occultation events, we would need the full 40 millisecond time resolution. So we would also need to store that data. So that's a big problem, or a lot of efforts has to be put into how to retrieve in a robust way the light curve in different time domains. So basically, to summarize, we've started the initial work on the GravityCam. Paper was published in PASA, I can't remember what the acronym is for, recently, end of last year. And we're building a test camera for doing on-sky comparison of the detector technologies that can be used for this instrument. The next step is to do a proper phase A study. It will give a better constraint of the instrument design and the number of detectors that is needed, the optimal design for that. We're currently trying to identify where to get funding for such a phase A study. We believe that the instrument design itself will be relatively simple, but will of course have a large number of detectors, but that there's a big effort needs to go into the software development, and that might be the biggest job on this instrument. We believe that as it should be a fairly simple instrument to build it, we could build the whole thing in about 3 years, and also produce the software needed and have another year, a full year for commissioning. Although the detectors, the number of detectors will be a major driver of the cost, we estimate about £50 million for the full instrument, with £500,000 a year in running costs, as we need to manage the large flow of data output. So that was all for me.
Okay, questions on GravityCam?
I love the idea of happening upon asteroids with rings by luck. It's sort of lucky imaging. That was neat. I wanted to ask about the EMCCDs. You mentioned that they don't suffer from the brighter fatter effect, like long exposure instruments. Is that really true? Because surely there are a lot more electrons, and you presumably scale everything or set everything up so that some pixels are roughly have the whole well depth filled, just faster.
Well, yes. So we would be running. So the idea is to use CMOS devices, which doesn't have the multiplication effect.
On CMOS, sure.
Yeah. So we would. That's why we say that we shouldn't have the high the brighter fat effect. We would collect less photons for each star. Yeah.
Just perhaps to come back to that particular point, you don't get up to very high signal level when you're running at 25, 50 frames a second, just because even a bright star isn't going to produce many photons. So the brighter fatter effect is when you get to a significant fraction of full well. And with the EMCCDs, in the imaging area, we will get nowhere near that unless we find ourselves accidentally looking at Jupiter, in which you get everything we deserve.
Thanks. Any further questions? No, thank Jesper again.